Okay, so here we are again. Another question to solve. Convert binary search tree to sorted doubly linked list. So this should be interesting. I don't know about this one. I'll just admit it. Excuse me. I am kind of afraid. Anything involving binary search trees, anything involving doubly linked lists make me uncomfortable. And then combining the two, I'm just immediately uncomfortable. I am immediately uncomfortable with both of these things. So we'll see how this goes. This might take a while. This might take a while. Okay. Convert a binary search tree to a sorted circular doubly linked list in place. You can think of the left and right pointers as synonymous to the predecessor and successor pointers as doubly linked list. For a circular doubly linked list, the predecessor of the first element is the last element, and the successor of the last element is the first element. We want to do the transformation in place. After the transformation, the left pointer of the tree node should point to its predecessor, and the right pointer should point to its successor. You should return the pointer to the smallest element of the linked list. Sorry, my mind started wandering elsewhere to other things. Circular doubly linked list. Oh boy, in place. I'm not sure what that means if it's in place. Think of the left and right pointers as synonymous to the predecessor and successor pointers in a doubly linked list. For a circular doubly linked list, the predecessor of the first element is the last element, and the successor of the last element is the first element. Excuse me? The predecessor is the last element, and the successor of the last is the first. Okay, I guess that makes sense. When it is in place, so the transformation, the left pointer of the tree node should point to its predecessor, right pointer should point to its successor. You should return the pointer to the smallest element of the linked list. Great. Head, okay, 1 points to 2, 3, 4, 5, 5 points to 1. And all these point backwards as well. Oh man. Look at these pictures. Shows the transformed binary search tree. Solid line indicates the successor relationship. Dashed line means the predecessor relationship. Okay, 1, 2, 3, 4, 5, 1. And there's also pointers going backwards. Input is empty tree, empty linked list. So, so basically we're gonna just really mess up this tree. It's gonna be great. Okay. Number of nodes in the tree is in this range, 0 to 2,000. The values are between -1,000 and 1,000. All the values are unique. Okay. It shouldn't be too bad. I say that, but I'm like, should be like, what do you call that? Not shaking or shivering, but like nervously. Shouldn't be too bad. I'm gonna eat those words. I'm about to eat those words. It's definitely gonna be interesting. Yeah, so I guess what that means is we want to find, so the head is going to be the, oh, 1 second. Okay. All right, so the head is going to be the leftmost node. So we can just write like a quick while loop to find the leftmost node. That is sort of the starting point. Now what's tricky about this is basically this is an in-order traversal that we're going to perform. And as we perform the in-order traversal, we also want to build the linked list. So the question is, we could do this recursively, I think. It's just, how do we want to do that exactly? Where does the, so, okay. Suppose we create the doubly linked list in the left subtree, and this node, and then we have the doubly linked list on the right subtree, right? So that'll give us our in order traversal 1, 2, 3. What we want to do at 2 is make the left, so 2 is already in the right spot, right? The left node, its left tree is already pointing to 1, and its right is already pointing to 3. I think the issue, one of the issues is that 3 needs to point back to 2, and also 3 needs to point to 4. So what I think we probably want to do in our recursive routine is return the last node, or the tail node, basically. So I could point that tail node to return the tail node, and we want to point that tail node to the in order node here. Same thing, this 3 points to this 4, right? The right pointer. And we actually don't need to modify, I think, the other pointers. Yeah, I think it's only basically this just needs to be threaded. We do have one issue though, where the final tail node of our recursion, we need to point that back to the head, so the right node will come back, right? And there's a right node that comes back to 1. That's sort of the final tail node, and then there's one issue where the left node doesn't have a pointer for the head. The left pointer has to point back to the 5 too. So that's the left pointer on 1 and the right pointer on 5. So these will just get extra pointers. So I think it's actually relatively easy. I think it's okay. Again, I might eat those words, but so we're gonna say obtain pointer to the new head node. So we'll say while we could do this. It's kind of nifty. For pointer p equals root. P exists. P is going to be pointing to its left, and we're going to say we have P is root and previous equals root, and P equals root, and we're going to say previous equals P and P equals left. And actually that's all you'd have to do, right? Because this will eventually be the null pointer, and then you actually want this. It's actually that simple. It's all the way on the left side. Okay. New head node. And then we'll call it new head. Oh, oops. Okay. Now we have in order traversal. It's probably the simplest way to do it is write a recursive in order traversal routine. And we'll have a node P, or R, we'll call it. And we want to return a node pointer. And there's some manipulation here, so we'll say after in order traversal, destructive in order traversal. Performed. Sure that the head node, the tail node of the linked list connected to create a circular linked list. That's the last part we have to do here. In between here though, we're going to say Okay. So we actually have to call that routine. So call the new tail. All right, so this returns the tail. We have a base case. So if R, or if not R, return null pointer, I guess. I'm actually not entirely sure here. We'll come back to that. We'll come back to that in a moment. What we want to do is call this on the left subtree, which is going to be R left. Call this on the right subtree. So this is like the general form, and then we're going to operate on the root node here. So it's kind of like the general form for an in-order traversal. You do the left tree, then the left tree, the head node, and then the right subtree. So call this the left tail. And what we want to do with the left tail is we're going to basically create a doubly linked list of the left subtree. We're going to take our left tail and we're going to point the right node to our root, R, right? That's going to be operating on that node. Our root, R, is also already going to be pointing to the doubly linked list, I think. Is that right? Not necessarily. No, it should be pointing to the, yeah, okay, I see. So, and R left should be pointing to the left tail. Okay, yeah, you do actually need to modify these because, excuse me, because there's some head node here that this is on this left subtree, and now we want to actually point this to that new tail. So this left pointer will point to the new tail, and the new tail's right pointer is going to point to this in-order node, this new root. And we'll just suppose this is a doubly linked list recursively on the left side. Similarly, on the right side, we also want to we have left tail, right tail, we'll call it. Creates a doubly linked list on the right side, and we want to take it's actually not the right tail anymore. It's going to be, so that's kind of interesting. We actually want this left node. We actually want the head of that new linked list. That's a little bit awkward. I think it's not that big of a deal, but yeah, we actually want the head of that new linked list because we want this. This actually, by the way, this is very similar to threading a binary search tree or just a binary tree, just in general. I want to say this is the same thing as threading, actually. It's very similar. Basically, this allows you to perform anything that was otherwise like a that would be like a recursive what do they call that? Like a recursive in-order traversal of the tree. You can use this routine to thread it, or something similar to this, to thread the tree, and then you would have a actually no, that's not entirely true. I'm sorry, that's not quite right. This is not the same thing as threading. This is similar, but not the same thing. Basically, this would create like a sequence, so you can walk through the elements left to right, iteratively. But it's not really. No, it's not the same thing as threading. It's not the same thing as iteratively traversing a tree. There's a little different doing that. It's very similar, but it's not the same thing. Well, we know what the new head is going to be on the right subtree. It's going to be the leftmost node again. So we would actually return this right tail, I think. Just copy this routine. Oops. We'll call it new head or right head. Yeah, new head is fine. That's okay. Call it, excuse me, R right. R right. And then we just say if R right exists. Really, you would do, because this might not be the, this might not, oops, this might not exist at all, potentially. And then you would say the left side is going to point to R, and R is going to point to, eventually you'll say R, well, let's see, let's do it this way. If it exists. So this can become a little more complicated than I was expecting it to be. And the new head left, and then so R right is then going to point to this right subtree. Actually, it's going to point to the new head. Yeah. The reason why you want to do this is that this right subtree it's gone. Once you point this R right to something else, you won't be able to access it again. So then you operate on this right subtree. Yeah, this is a little bit funky. I'm not sure about this actually. This is a little odd. Let's see. We perform left subtree. We make that a doubly linked list, and we get the tail. Point that back to the head. Right subtree. Again, it's inductive or recursive. That becomes a doubly linked list, and we get the head. We start with the head before we perform this procedure, and we point that head, the new head. We point, kind of set those operations correctly, right, or pointers correctly, and then we recursively create a doubly linked list out of that right subtree, and we actually want to return the right tail. After all of that, and we still have some operations afterwards to make it circular, but that in theory will give you the doubly linked list that we're after. I do believe this will be linear. Yeah, linear in the number of nodes. I think so. Yeah, I think so. Some issues that you'll run into though. I want to say it's actually, it might be n log n. It might not be linear. The reason is that I think at each subtree, you're going to dive all the way down to the left side every time. No, that's not true. No, I take that back. No, we're fine. At each subtree, you're going to take the, yeah, no, we're fine. You're going to go on the right node's leftmost, the right subtree's leftmost node. This is definitely confusing. I realize. It's definitely very confusing. I want to say something like the base case we have to look at, right? Also, how are we doing on time? Yeah, 20 minutes, okay. I don't know about this problem. This is kind of a tricky one. This is kind of involved. The base case, we don't actually want to return a null pointer ever. Call this an edge case. But really we want to say if this is really the base case we want, which is if we're looking at a leaf node, then we don't want to operate on the leaf node. But sometimes we do get, like you could have an empty, you could have a right subtree that's empty here on 3. Oh man. Oh man. Let's see. Okay. So. Sorry, I just had a thought, like, oh man, I've suffered a lot of loss lately, and I'm just, the past few years, I'm just like really upset. Sorry, it's hard, it hurts, it actually hurts. Every now and then I think about it, it's like, oh man. It's all my fault too, that's the worst part. It's like, yeah, all these poor decisions. Had these really lucky things happen to me and then just ruined them. How am I ever gonna get back to that point? It's like, it's gonna take you forever. It's gonna take you forever if you ever get back to that point, if ever. Anyway, so what I was saying was have this edge case, base case. Yeah, I kind of want to return the leaf nodes, but no, there are cases where you would operate on the right subtree. It's kind of tricky. It's really intended to operate on something that exists. Because we want to return the tail. Yeah. Basically, I want to say that if there is no right tail, if there's no right subtree, then you'd return the node, this head node. Yeah, I think so. Yeah. Yeah, I'm really sad. Actually, really sad. Just thinking about what I did. I did these things that were just really rough. Just rough. So you pretty much don't want to operate on a right subtree that doesn't exist. And then left subtree, yeah, you assume there's always a tail. If there's no left subtree, you don't operate on that either. Should not. Yeah, I'm really sad. I'm really sad thinking about it. It's like, that's brutal. That's just so difficult. Really, really difficult. Yeah, just I really screwed up. I really screwed up. So if there is a left subtree, then we want to operate on that recursively. If there is no left subtree, then pretty much this node is the left yeah, it's not really left subtree, but it's the head. I mean, we don't need to return this though either. We don't need to do anything with it. Only really care if there is a left subtree to operate on. Yeah, pretty much we'll never operate on a node that's doesn't exist, right? Just keep things simple. Also, if there's an empty list, right? I had that one in the test cases. That was kind of nice that they added that, because my code probably would have missed that case also. All right. So now we can assume that we actually have things to work with. So this new tail, in order traversal is performed, ensure that the head node and the tail node linked list are connected to create a circular link. So now the head node, this new head, left, the new head left should point to the new tail, and the new tail right should point to the new head. So the new head goes to the tail, and the new tail goes to the head. Yeah. What happens when we do this? What happens if we do this? It's like, no way this works. Yeah. There's no way this works. There's so many things that can go wrong here. Okay. Yeah, I would just get destroyed in an interview here with this. Oops. Yeah, a problem like this, question like this would just be really difficult. It's 4, 3, 1, 2, 3, 4. Okay, let's see where does our runtime error happen. Oh wow, whoa, okay. Oh, no kidding. Oh, really? Alright, so it runs into an infinite loop somehow. Wow. Really? I was not expecting that to happen. Huh. So if there's a left subtree, if there's a right subtree, operate on the right subtree. So I guess we call the left tail over and over again. So somehow we got ourselves into an infinite loop, which is a bit awkward. I'm not sure exactly how I did that. Yeah, this is kind of transformed from just a simple in-order traversal to something a lot more complicated. Don't know if this is going to be... Yeah, oops, that's not what I wanted. Alright, we're over 30 minutes, okay. We'll probably get another 15 minutes during an interview, but I don't know about this one, man. Left subtree R left. If there is left subtree, take the left tail R left. So sure, so we get the left subtree here. Alright, if there is a left subtree, operate again. So operate on this guy, go down to the left side. Operate on this guy. Say there is no left subtree. So we continue. Say check out the right subtree. There is no right subtree, so return 1 as it is. Okay. So say left tail, which is 1. It's going to point to the root, which is 2. Right 2 root 2 left is going to point to 1, which it already does. And we continue to operate using it, we'll say. I have this right subtree, which exists. New head is right. Okay, so we get this new head. I go all the way to the left, and immediately P goes to empty node. So now new head is pointing to 3. Left goes to R, which is 2. And R right points to this new head, which is 3. So that's perfect. So left, right. And then now we right tail on F on the right subtree, which exists, right? Oh, we gotta be really careful. So now we operate on this right subtree. It says return right tail. So we have, there's no left subtree, there's no right subtree, returns itself. So this should actually return 3. So we should get 1, 2, 3 now. And then, so this returns, so now this was that left subtree that we performed before. That left tail is this guy, so it should be 3 that we get for the left tail. So left tail right points to R, which is 4. R left points to left tail, which it does. And then we operate on the right subtree. And so new head is this right subtree. I don't know, man. This seems like it should work fine. Okay. Okay, how do we get here? What happens here? Oh boy. What do we print? 4, 2, 1, 3, 2, 1, 2, 1, 1, 1, 1, 1, 1, 1, 1. So 1 ends up making a circle for itself. Okay, that's not good. How did that happen? So I guess we went to this left subtree here, and we said left tail, which is operate on R left, right? I don't know if that matters. Maybe that matters. No, I don't think so. So we operate on this left subtree and get that left tail, we'll say, recursively. But let's say, yeah, let's say we operate on this one. So this is R, right? And there is no left subtree here, so we'd skip this. And then there's no right subtree either, so we'd skip this. So we would just return R directly. So I don't know how. I don't know how we got. Maybe this being used multiple times. No, it should be. Just call this head. I don't think that matters. That shouldn't make a difference. I mean, hopefully not. That would be really confusing if it did. Oh, that was the problem. You're kidding, really? Wow. Oh, that's interesting. Whoa. So this new head actually had priority over the local variable. Wow. Okay. Learned something new about how the closures work in C++. That was really subtle. That was extremely subtle. I would not have caught that. Okay, we don't really need this anymore. Well, actually, hold on. What does that look like? 42135. Not a valid circular doubly linked list. No. It's so close, though. Stiff. Alright, we're at like 40 minutes. Okay, we'd have like 5 minutes to fix this error, which it would take me a while because I'd actually have to walk through this by hand, and I probably wouldn't be able to do it as quickly as just pressing the run code button. So I probably would not have passed this interview. I don't think so. Yeah, definitely not. I also wouldn't have caught that error there with the head. It's very subtle. So they're saying this is not valid. Why not? What's missing? They're not saying it's not circular, they're saying it's just not valid. I think the issue might be that some of these nodes don't point back properly where they should. Really. We could debug, I think. Yeah, sure. Do new head. So for actually head p, or do p not equal to new tail. Yeah. And p equals p right, let's say. And then we're also gonna p or val. It's gonna be p val. And we're gonna say left. It's p left val. P right val. And this should actually throw a runtime error. And the tail. We just want to print the tail too. So yeah, this should give us a runtime error. Yeah. Because we're gonna either, yeah, we should get a null pointer. So 1 points to 5 into 2, which is correct. 2 points to 1 into 3, which is correct. 3 points to nothing. Ooh, 3 should be pointing back to 2 on the left side, and right side should be pointing to 4. Okay. So how come 3 doesn't point back? How did that happen? Oh, we don't have the ref. No, there's a right subtree here. This right subtree. This new head left R, right subtree head. Oh, that's why. I missed one. Of course. Super subtle. Whoa. Okay, what happened now? Now we have a... Oh no. Oh no, this creates an infinite loop. Oh. So I take it back. It had nothing to do with the closure. No, I was fine with the oh wow. Okay, that makes your head spin, huh? The closure was fine. The issue is this creates an infinite loop. One way or another, this creates an infinite loop. So now 1 left points to now somehow 1 ends up being the right subtree? No, that's not right. How does 1 end up being a right subtree? Points back to 2. That's really confusing. What happened? What is going on? Debugging recursive things is great. Okay. Lots of fun. 3, 1. Okay. So why is 3? Okay. So this right subtree was 3. Okay. And then had this right tail, right subtree for 3. That should get returned. 3. And 2 should be, that was the right subtree for 2. How did we end up with a, where did 1 come from? What's going on? When, huh? How much time we have? Yeah, okay, we're gonna go over time, I think, a bit. All right, fair enough. What is going on here? Where did 1 come from in the right? So when is 1 a right subtree? Is that somehow we put left tail? I'm so confused. I was so confused. Excuse me. Is it actually using the wrong head? Is this actually... does it have something to do with the closure? I don't think so. I don't think this has anything to do with the closure. It shouldn't matter. I think we're running the same issue anyway. Yeah, it should be... Yeah, the local variable does supersede this outer variable. Absolutely. That's what I thought. I was like, what? That's not... Oh, wait. Oh, maybe not. No, yeah, yes. Really confusing, but I don't know what I did wrong here. It's awkward. That's awkward. Test 3, test 1. What is going on? Yeah, I don't think I would do very well in an interview on a question like this. That would suck. I think I would need more, not just more practice. I think I would need to see like a better solution and use that approach next time. 4, 4, 4. Okay. That shouldn't be happening. Why are we getting... What is going on? Why is 4 being repeated a million times? 4, 4, 4, which doesn't make sense because you would call this once, and then you have a left subtree, you have a right subtree for 4. On this left subtree, which is our left, should be 2. So really, why? What is going on here? Shouldn't this call? Oh, that's why. Excuse me. That's my mistake. Did I actually accidentally use root where I should have used R? It's possible. Anyway, yeah, 4, 2, 1. 4, 2, 1, and then 1 finishes. We come back. We process 3 next. We test 3. All right, so this head is 3, and the head left is going to point to 2, and then 2 is going to point to 3. Okay, and we go back up to 2, and we already processed 3, right? So now we're processing 4 is going to point to 2. So test 3, 3 val. Now, oh wait, where's this 2 coming from? 4 points to 2. The right subtree for 4 should not be pointing to 2. See, that's a question. How did that happen? What happened there? This should be going to, this should be finished in the right subtree for 2, right? Just returns 3, that right subtree. And then we say head left equals R, R right equals head for 2. And then the right tail, we would return 3 again. So right subtree on 3. This actually, oh, this returns 2. That's why. What is going on? Excuse me? Hold on, what is this? Huh? What happened here? I don't think I ever get to this line. Yeah, that's the problem. Okay. Okay. should get interesting here. This should be interesting. See, this is where it gets stuck. Excuse me, test 3, R right value is 3. Whoa. So 2 is R. R value is 2. Right subtree is 3. Okay, interesting. Whoa. Wasn't expecting that. So now we operate on this right subtree. We don't get this tail, right? We operate on 3 now. We say there's no left subtree, but is there a right subtree? Apparently the left, oh, because 3 is pointing back to 2. That's the problem. Yeah, I see. I see. Okay. So now we operate on 2 again, and then now we end up in this loop, I guess. That is so confusing. Why did we... Oh, no. Why are we looking at the right subtree again? 2... I think you do this. I think you do this after you look at the right tail. Yeah, that's my mistake. Update the new head node of the right subtree after the right. After and only after it's processed. I realize that might be a little confusing, but the reason for that is you don't want an infinite loop. Now it works fine. You gotta be kidding me. Determine the new head node. Now it works fine. Now we have no problems at all. We are just peach keen after that. I mean, of course. Wow, it only took 54 minutes. Nice. Okay, tree visualizer. Let's try some other test case. Oops. I need binary search trees. Actually, we should probably get a few of these going. Try that one. Very good. Try one with a couple of elements. I don't know what these look like. What's 4, 5, 6 look like? The upshot to operating on trees is that pretty much if it works for one tree, oh wow, look at that. That's not a binary search tree, is it? No, it's not. Actually, is 4, 5, 6 a binary search tree? No. There we go. Yeah, the upshot with trees is that usually if it works for one case, then because it's sort of recursively operating on the trees are sort of like somewhat like a fractal almost trees. So if it sort of works on one set of trees, probably extrapolates to all of the whole set of trees. So let's put gotta make this in order, right? So we probably need, I don't know, where's 4, oh, we should probably just do 1, 2, 3, right? 1, 2, 3, 4, 5, 6. Oh, that's interesting. It's an in order it's an in order traversal. You see that? A level order traversal. That's interesting. 4, 5, 6, 7. It's probably 7 should be over here. Oops. And then 1, 2, 3, 4, 5, 6 should be on the left side, I think. I guess it'll be 4. And then probably 1, 2, 3. Something like this. 7, 4, 2, 1. I don't know. Wait. What? Oh. Where's 2? 2 is here. So this should probably be 1. No. 3, 4, 5, 6, 7. I guess this would be 8 here. 2. Where 8 is, we'll put a 1. Where 9 is, we'll put a 2. Where 2 is, we'll put a 9. 3, we want that to be a 5, so swap 5 and 3. 10, no. Actually, I think 10 should be 5. Oh boy, this is fun. Oh no. 5 should be swapped with, yeah, and then 10 should be 6. So 6, 10 isn't 10 over 6 is. And then 11 should be 7. So put 7 where 11 is. I put 11 where 7 is. I guess that should be 8. Where's 8? 11, 8. So this is quite the algorithm to get this to be what I want. So where's 3? 3 and 9. 3 and 9. Okay, so 1, 2, 3. No, actually 3 and 2 should be swapped now. 2, 3. So we have 1, 2, 3, 4, 5, 6, 7, 8. Now 9 should be where 11 is. 11, 9, 9, 11. 10 should be where, no, this has got to be, oh, we got to fit a bunch of things in here. 8 should be 9 where 12 is, actually. Is that 9? Make that a 12. And then 9, 11 should be 10. And then 12 should be 13. So 13 and 12 should swap. And then finally, 8, 9, 10. Oh no, 11 and 12 should swap also. Alright, let's give that a shot. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13 gotta swap too. Alright. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There we go. Okay. Now that's what we're expecting. That's correct. Okay. I guess we just go for it. I don't know. I guess we remove things. So we can remove 13. And 5 is still not really in the right spot. I don't know. I don't want to mess around too much with the test cases. I'm afraid to hit the button. but I think we go for it. Oh, hey, we got there. Sweet. Not bad. Wow, we're super fast. Let's try again. Give it one more time. Okay. Interesting. That's pretty slow. Alright, whatever. That's enough. Okay, that took forever. I don't know what to say about this one other than it's not the cleanest thing. I think I had the right idea, just implementing it was really awkward. Had to go through a bunch of test cases too to kind of hash out the issues. That was over an hour. That would have been a failed interview question, I think. Also, it's time for bed for me. But how could we need to improve on this, I think. Not just like on solving this particular problem, but a problem like this in the future. I gotta figure out a way to like break problems down properly, I guess. So they're more easily. You know what? Excuse me. Actually, the main issue is this. I think this got me caught up for like quite a while because I didn't see it. I think otherwise we were in pretty good shape. I actually don't know about this problem. It seems kind of hard to do quickly. There's like a lot of snags and things. It's not just a simple in-order traversal. It's similar to an in-order traversal, but it's got a lot of extra things going on. This is kind of what I was saying before about doubly linked lists. Like they're just kind of a nuisance to deal with. Both trees and linked lists can be really challenging. But this is a reasonable solution. It's maybe not perfect, I guess. It's okay. I mean, it's okay. I think it's okay. Yeah. Yeah, this caveat here helps. I think it's okay overall. I think I did alright. It's tricky. Definitely really tricky. This order of operations here mattered a lot. That took a while. Making sure that we only operate on leaves, things that exist. That was kind of significant. Normally you would put that over here, but because we wanted to return something that we knew was never null, that was kind of important. Have this else here. This doesn't return anything to operating the left subtree. Yeah, kind of. I think this is okay. Would I get it right on an interview? Probably not. Would I get this within an hour in an interview? Probably not. Yeah, that would be really hard in an interview. In theory, it could be done, but I think in practice, it just really would be hard. Okay, let me go. So yeah, that'll probably be it for me tonight. Thank you all for watching. I hope you enjoyed yourselves. I will talk to you soon. Have a good rest of your night. Take care.